I have a suggestion. So now we have about 15, 20 minutes or something left. Should we open the discussion up to the morning session, so it is our current speaker and the two other speakers, so we could have and one way to do that, I mean, we had, just to remind you, we had a discussion of sort of all the theoretical and practical problems about self-replication. We had talk about how you can model self-replicating systems, using molecular dynamics type processes, and now we have a discussion of sort of these cosmic issues of the composition of the solar system. I'm not sure what the common denominator is, but certainly, you know, we need carbon to create life as we know it, and it's certainly still a complete mystery to me how all these things fit together and how we end up with the right composition, so we can actually start to make self-replicating units. So I don't know who wants to take the first stab at are there some specific questions? Yeah.
It's not a question to combine these things. I don't know how we do that, but I guess that we get a little bit around the trees time. So I have two more questions to call here this place. I would like to know, first of all, what is your conclusion from the fact that you don't find iridium in Greenland, but you do find iridium in Tunguska? That the explosion was lower, or was there another?
I mean, there are many things I don't understand. That's one of them. But I do find very little iridium in Siberia.
Yes.
Unexpectedly little.
Yeah, but
so maybe I'm just below my detection limit. That could be. I have a detection limit in Greenland. That's a very ideal condition. The center of Greenland, you have very little stratospheric dust coming in. You have very clean environment, and what we do is we take away all the precipitation, we take away all the water, and just have. And we can see that we have 1 per mil of cosmic material. It's very good compared to any other way of sampling. And the detection limit of iridium went down to femtograms, which is only like what's that? 10 to the power 7 away from Avogadro's number. It's a very, very low detection limit.
So 10 to the minus 15 grams iridium per gram of dust.
Yeah.
But excuse me, that iridium, does that have anything to do with that explosion? Iridium is I mean, how do you think iridium is formed from the thing? I don't think it can have anything to do with an explosion in the atmosphere.
No.
I mean, it's an R-process element that's formed in supernova. So how can that be?
That's why it's present in meteorites and not on Earth.
Yes, but
no,
Uwe said it had something to do with the explosion.
Yes, because the fact is that if it explodes low, if actually this 8 kilometers in which it's assumed to explode, this is just the stratospheric limit. So if it explodes above that, it spreads all over the globe. And if it explodes a little bit below that, it will spread in the area over the explosion. So one explanation for finding it in Tunguska and not in Greenland would be that it actually exploded low. So that all settles in Tunguska. That was the solution.
I thought you meant the explosion energy or something.
No. Yeah.
No, but the point is that even, I mean, if you would make an explosion of 12 megatons TNT at 8 kilometers height, it will make a huge plume into the stratosphere. There's no way that you will not inject a substantial amount, maybe half of the impact material, maybe a third or something like that, into the stratosphere.
It would be true even if it would be lower altitude.
Oh yeah. I mean, even if you made the explosion at 12 megatons TNT, that's 650 Russian bombs. Even if you made it at ground zero, I mean, even if you made it zero height, it will inject an enormous amount into the stratosphere. And so on top of that, if you let it explode in 8 kilometers height, there's no doubt. Obviously, you could make a suggestion that half of it went to the ground directly and half of it went upwards. something like that would be realistic. So the point is, there is very little iridium in that impact, and that is disturbing. It is a disturbing finding. Even, I mean, some of my American colleagues have attacked me for the carbon calculation. Even if you take that away and just look at the pure iridium numbers, that is disturbing. Very low in iridium, that impact.
So
And
that
then
was
there's
actually my
no
next
way-
question, if I may continue.
Sure.
Yeah.
That it was exactly this. So what do we learn from this about comets and CI?
Yeah,
So
I mean,
one thing we learned that is that you have the C12, C13 ratio, the same as in carbonaceous convex.
yes.
But this we should expect, like either if, independent of whether it was a CI contact or it was a comet,
Yeah.
because it's the same kind of unprocessed material.
So it's
So this is-
unprocessed material. That's what we can
So
conclude.
that's the only thing we could do.
Yeah.
And then from the iridium, we may conclude that it's not a carbonaceous chondrite because it's so different from carbonaceous chondrite.
Yeah.
And it's not known in general from comets. So there may be a hint that for comets, for some reasons it's very different. And
Yeah.
that may indicate that in the outer part of the solar nebula,
You
there
didn't
was
have
something
that.
different.
Yeah. That you didn't have that contingent of iridium that you have in the inner solar system. But that would still be a major. I mean, that would be a major event, milestone in the understanding of the solar system, if that's true.
But it could be consistent with this chemical condensation models that methane you will not have included in the carbon from methane you will not have included in the carbonaceous chondrites, and the carbon from CO will not include either.
Yeah.
So you will have out there, if it's a comet, then you will have much more carbon and the same amount of iridium.
Yeah.
So what would be very interesting to see that was iridium compared to silicon or iridium, to know whether it's iridium that is down or it's carbon that's up.
It's carbon that's up.
It's carbon that's
That's
up.
the other references I talked about. They get a few other elements, and it certainly looks like it's carbon that's up.
But they were all noble metals which have the same kind of condensation pattern as iridium.
Yeah, but not as clear cut as iridium. It's not as easy. Gold is factor 10 down compared to iridium. So it gets more and more muddy the moment that you approach Earth crust values, and you approach, because then you have dust there also. Normal tropospheric dust comes into the Tunguska area. This is positive there too, and that goes into the analysis too. So it will be more and more muddy as you go to elements that are less enriched in cosmic material. But gold obviously is good. It's a factor of 1,000. Nickel would be another element that would be the next element that we look for. But it is, I mean, I'm not saying it's not disturbing. And I'm not saying that I understand it.
Regarding astrobiology, there's from impacts in general, first of all, two different implications. One is from meteoritic impacts, perhaps also cometary impacts, is the question of mass extinctions. So that's maybe an issue that should be discussed at some point. Another aspect, more relevant to your talk now, is the question of if you have cometary impacts, very weak ones perhaps, what are the ways of detecting and verifying this? I mean, Godfrey will later in this afternoon talk about the impact that where he has acoustic evidence, if I understand correctly, only acoustic evidence of the cometary impact on the 25th of July 2001. Right. So now, given your expertise and the chemical modification of the upper stratosphere that you would expect, what would be the type of analysis that one should actually do in some similar events, either in future or perhaps even a posteriori?
Well, that's very difficult to say. I mean, obviously, we would attack this as if it was a meteorite impact. That means we would go ahead and detect iridium. We would go ahead and detect as many isotopic ratios as we can. That means density 13, that's 18 if we can. Rare earth element fractionation patterns would be an ideal thing to do. But, I mean, if we don't trust that we know the composition of comets, we really deep problem. I mean,
So that's something which one could perhaps even detect afterwards in the rainwater.
Yeah.
Where you have samples of your rainwater. So
Yeah, it's there. And I will show the some mass spectroanalysis, some several viral elements are there. So I can look at that and make out something about that.
but have you measured the delta C13?
No,
Is
that
that
is
possible?
not done.
No.
This mass spectrum was taken by another agency who initially did that. So I have that data with me. I will show that. So some 25 elements are there in part of the unit quantities. Carbon is some 50% carbon.
Yeah.
So I was wondering whether a normal biological material contains so many rare earth compound elements. So I will show that slide.
I had a general question on iridium, which is maybe just due to my ignorance of geology. So iridium in the earth sinks deep. If there's iridium in the mantle, could you see some in geologically active regions, say in volcanoes or in places where you had basalt floods millions of years ago? Do you have any measurable quantities of iridium?
Of iridium coming out of volcanoes?
Yes.
Yes. It has been it's been sought after very much because the Cretaceous Tertiary event research has sort of made two camps. One camp that is now winning, that says it's an asteroid impact, but for 15, 20 years there was also a fraction, there's still people left of that fraction that believes that there was no impact, that it was just a coincidence, that evolution, that it was, see, I'm not a biologist, but the way they explain it is that evolution came to a certain point where species were so specialized that they died out.
Sorry, didn't you ask about...
Yeah, I'm coming to that. I'm sorry. I'm just okay, so they say that you just had a natural or a systematic die-out of 50% of all living species on Earth 65 million years ago. Therefore, they have to find another explanation for the iridium that everybody goes and finds. It's been found over 60 localities over the Earth. Denmark, 3 places, Sweden, China, Italy, America, Montana, Canada, whatever. And so they have to find another source for that iridium. And they have been looking at volcanoes very drastically and see if they could detect iridium in any volcanic eruption. And there was an eruption at Mount Kilauea in 1986. There was a tiny little burp of that volcano. And at Hawaii they have this mid-atmosphere observatory where they have a vacuum cleaner and a dust sampler, and they would every 2 days or 3 days they would change that filter and analyze it chemically. And in 1986 one of the filters showed an enrichment in iridium.
But by how much?
Very small, like 0.1 nanograms. Very, very little.
Wasn't there actually, I think a few years, within 10 years, less than 10 years ago, I thought some people have claimed from the Mir space station observations that they actually have seen an impact, actually an arc of an impact with a radius of 200 kilometers, maybe a diameter of 200 kilometers, near the East American coast, southern East American coast.
That's the Tutankhamun or the
That's 65 years ago, right?
Yeah.
Yes. So that's...
No, I don't understand that. You say that from Mir?
Or whatever, yeah?
Yeah.
What, from space.
They saw what?
They found a crater, the impact crater,
Yes.
in
Really?
Yucatan. Yucatan impact crater was seen from, was found from space.
See the picture, yeah, it's a fourth color
That's
picture.
because they knew it was there, right?
No, nobody atoll.
Okay, I mean, the story of how Yucatan was found, that's also very good. But that
Yeah.
started in 1956 by Pemex, the Mexican oil company.
Uh-huh.
And there were 2 American geophysicists down there. And they made drill cores out there the Pemex, the Mexican oil company, made drill cores there. And then in 75 or something like that, an American geophysicist sat in Houston reading the report.
Mm-hmm.
And then he said, the report said that they were drilling and drilling and drilling, and suddenly they found something that looked like hard rock in the middle of this carbonaceous package there. And the way they described it, it looked like a meteorite. And so he went down to Mexico and tried to recover that piece, because that was put in the warehouse. Well, the warehouse was burned, and then he went out into the jungle there and tried to locate the drill site. And after a lot of beer drinking and so on, the local chief pointed the place to him. It was now a pigsty. And it had like 8 feet of manure on top of the original pit. And it's a good story. And they started digging. They were real geophysicists, okay? So they started digging, and they found nothing. I mean, that's real science. After digging 8 feet of manure, they found nothing. Okay? And so they went back to Houston, and somehow they got, the Mexicans and the Americans got together and drilled the core and found a meteorite. It was on the front page of Nature, and real meteorite, just drilling down there, and they dated it, and it was 64.89 million years old. It was just head on. They found a meteorite, it was the right age and everything. That was when they found the crater.
Yeah, but you know, as the other group says, it could have come 1,000 years after all the dinosaurs already died, right?
Yeah,
Because
that's
the dating
true.
is not that
Yeah.
exact.
No.
So I mean,
But the
it was
fact
there,
that
but it might not have extincted.
Yeah.
I mean, it could have come afterwards.
but the fact there was an impact crater at Chicxulub, that has been proved, I think.
Okay.
But whether or not it is connected with the extinction event, that's a much more difficult question.
I have a question concerning this outgassing of iridium in volcanic events.
Yeah.
How you
Yes.
describe it, it sounds to me a little bit complicated. It is not just sitting in basaltic rock so that you can just say,
No.
it is in gaseous form that it's
Yeah. It looks like it's in a very, the compound has been described, I don't remember it now, it's something like, it's a very special compound, and it's only stable for a very limited temperature range and so on. It's very bizarre.
okay.
But obviously there are iridium mines, so there are rare places like the diamond mines. But you know, when you go out and dig in the ground here, you don't find any diamonds, right? You have to really know where to dig for it. And it would be nice if it was in active volcanic regions, but that has only been established once. But people are desperate to try to prove that, because they want to prove that it was not an asteroid that hit Earth. So a lot of effort has been put into that. And I think when so much effort has been put into it, and very little comes out of it, it's a very good proof. It's a negative proof, but it's very good.
But wouldn't it, I mean, if you don't think meteorites and things, just think Earth, wouldn't it be interesting because it could give us some information of the convection and how things, move around underneath the surface, the crust on
Yes.
Earth? Because, I mean, the iridium is going to be down deep, so if we see it in volcanic eruptions, then either the eruption, I mean, the lava coming up comes from very deep, or you have some sort of fast enough convection which can keep it floating at
Yeah. The question is how deep volcanism you can have. I mean, how deep are the roots of volcanoes?
I recently heard a talk of a geologist who has actually studied the Yucatan impact.
Yeah.
And one argument in favor of this, that the iridium layer was deposited by this impact, was besides you pointed out that it will have a global distribution of iridium all over the globe, it's still that there's a systematic increase of the amount of iridium deposited the closer you get to the impact site. I think this is a strong argument that it's related to this event and not due to some volcanic activity sitting somewhere.
Yeah, that is very true. One should just think why the other people say that. The reason is that the biggest volcanic event ever happened right around there, 5 million years before the Cretaceous impact. The Deccan Traps in India erupted, and that was enormous. I mean, it was probably the biggest volcanic event that has taken place on Earth in the last 1 billion years. So, I mean, it's not, unfortunately, it's 5 million years before the impact, but it took a while to produce the Deccan Traps.
And there's not 2 layers.
That has also been tried. A lot of people have been looking after 2 layers, and it was found in El Kef, I think, in Tunisia. But the question is whether it's just a shift or bioturbation. If you have a layer here and you have a little worm coming down and depositing material on top and so on. I mean, it's a long discussion. It's taken 25 years and a lot of bitter.
But there's this other perspective that I mean, whether it's a volcano or I guess I don't think there's any discussion that there was an impact, right? Is that question?
I think if you look at it now today, at least 95%, perhaps 98% of the researchers in the world believe that it was an impact on an asteroid.
Yeah, that made this hole in
Yucatan.
Yeah. But that's a different question from whether that was what really caused the
extinction.
The extinction,
yes.
Because it's also a well-established fact that from time to time we do actually get spontaneous extinctions.
Yes. And then people have been looking for iridium at the other extinction events, and at the Permian Triassic boundary, they have found iridium in China, one place.
Okay. So because now we seem to be in the middle of another mass extinction, which is, and so far, well, I guess we have problems, but that's not what
the main I guess even for your theory is still safe there, because it could have been an impact of something without iridium, which you just showed, I mean, or very low iridium.
Yeah. This is disturbing. That's why I'm showing it to you. It is really disturbing. What I would like to do with the Tunguska is that I would like to launch an expedition up there and have holes, one at the epicenter like we have now, just for doing it twice. We've actually done it twice already, but the third time wouldn't. I mean, it's so controversial that it should be done again. And then 10 miles away, 15 miles away, 50 miles away, 100 miles away, in order to see the deposition distribution.
What's the problem in doing that? Is it difficult to get that? Well, I mean, yeah, but it's not going to the moon.
You know how big the mosquitoes out there?
Anyway, I think it's a good time to go to lunch here. Thank you very much.